This video is a follow-on to the previous one, which talked about converting a non-deterministic finite automaton to a deterministic one. The difference this time is that we're going to look at NFAs that have lambda transitions, basically a free ride from one state to another without consuming any input. The process that we used before, called subset construction, is basically where we track all possibilities at once, and whenever we have multiple states we can reach with a single input character, we put them together as a set of states, and I call that a composite state, and that will act as a single state in the resulting DFA. And when we have finished tracking all of the possible movements through the original NFA by that process, the accepting states in the result will be any state that contains an original accepting state from the NFA. So let's do an example. This time we're going to have an NFA with a lambda transition, which represents the language A star A, C star B star. So our alphabet has three characters, A, B, and C. The lambda transition is between states Q1 and Q2. What this means is that whenever we enter Q1, we get a free ride to Q2. So when we're tracking movements in that conversion process, Q1 will never appear without Q2. They will be put together as a composite state. And we have an important term for that. We say that Q1, Q2 is the lambda closure of Q1. So the lambda closure of a state includes the state itself and any other states reachable by one or more lambda transitions. They can be in a sequence. And we'll see an example of that a little later. So let's start the process. The initial state, of course, for this NFA is Q0. So that will be the initial state as we start constructing the DFA. So from Q0 with an A, we can see that we cycle, or we have the choice of going to Q1, but because of that free ride, that lambda transition, we can go to Q2 as well, simply by reading an A from Q0. So we get all three of them here. There are no out edges with a B or a C, so we're going to put an empty set in those places. And these will become jails in the resulting DFA. So now we have a new state that we have reached, a composite state, and we will track what it does for us. Well, following where we go with an A, again, we're going to hit all three, Q0, Q1, Q2. And how about with a B from any of these states? Well, the only one is at a Q2, but that is part of this composite state, so we have to say, where do we go? Well, we go to Q2. Now, how about a C? Well, a C only exits from Q1, but that's good. It's part of our composite, so we have to track that. And that cycles on Q1, but it gets a free ride to Q2. Again, the lambda closure of Q1. So we will add Q2 to our list, and it only goes to itself with a B, so that was easy to fill out. Now let's take a look at Q1, Q2. Where do we go? Again, there's no A exiting Q1 or Q2. Q2 with a B just cycles, and Q1 with a C cycles and gets that free ride. So no surprises there. And our accepting state in the original is Q2, so those last three states will be accepting. And so we will now have a DFA with 5 states because of the jail. And here it is. So let's do another example. Here is an NFA that has 4 lambda transitions, and some of them are actually in sequence, which is kind of interesting. So we have a lambda transition from Q0 to Q1, and we have one from Q1 to Q2. So that means that whenever I'm in Q0, I could just as well be in Q1 and Q2. And let's see, we also have Q1 going to Q3. And then finally we have this one from Q4 back to Q3. So let's begin the process. As always, we're going to put the start state of the NFA with the at being the start state for the DFA in the process. So the only problem with that is we have to keep in mind those lambda transitions. So the start state we're going to use isn't just Q0. It is Q0, Q1, Q2, Q3, because the lambda closure of Q0 is those 4 states. I use the capital lambda letter for the lambda closure. So the lambda closure of Q0 is Q0 through Q3. We might as well look at all the other states and see what they might have for free rides. Well, for Q1, we can reach Q2 and Q3 with lambda transitions. So that gives us that. There are no lambda transitions coming out of Q2 or Q3, but Q4 has that free ride back to Q3. So whenever we enter Q0, Q1, or Q4, we will always be taking along for the ride those extra states. And our initial state is going to be the lambda closure of Q0. So that is how we're going to begin the process. So here is an update of our procedure. We're going to add lambda closure where it applies. The start state of the DFA will be the lambda closure of the start state in the NFA. And then whenever we enter a state, as we illustrated before, make sure we follow all lambda closures. So with the lambda closure of Q0 as our start state, we will now ask where an A will take us from those states. From Q0, we don't have an A out edge, but from Q1, we go to Q0, but we have a free ride back to Q1 because of that lambda closure. But not only do we have a free ride to Q1, as we mentioned, the lambda closure of Q0 hits all of those. So we're going to have all of those in this result. Now you might be wondering where the Q4 came from. Well, the Q4 comes from the fact that I have an out edge in Q1 with an A that goes to Q4. And of course, we have to process Q1. And so there it is. And so we're going to hit all of the states with an A from this composite initial state. Now, how about a B? Well, a B only occurs out of Q0 and Q2. And we're going to reach Q2 and Q4. But remember, the lambda closure of Q4 includes Q3. So that comes along for the ride. So I'll take those 2 states and add those to the list for continuing the process. So we'll ask where those take us, and you can easily see that with an A, we're going to hit all of the states again. And with a B, we're going to hit all of the things we could originally hit with a B as well. And so now let's process Q2, Q3, Q4. Now, in this case, Q2 doesn't go anywhere with an A. Q3 goes to Q4, but I get a free ride back to Q3 because that's its lambda closure. So that gives me that. And it turns out that a B is the same thing because from Q2 with a B, I go to Q4 with that free ride back to Q3. So I get that. Now let's process that, and we'll finish this up pretty quick. Well, with an A, Q3 goes to Q4, but I get that free ride back to Q3. Now, what about a B? A B does not appear in Q3 or Q4, so I go nowhere, so I have a jail. So we have finished. We don't have any new states that we have reached, and we're going to have 5 states in our result. And the accepting states will be those 3 states where Q4 appears. So here's the final answer. So we have the initial state, states Q0 through Q3, and then the state Q0 through Q4 will be this state here, and then Q2, Q3, Q4 here, Q3, Q4 there, and then here's our jail. End of story.